For the last video, we have talked about all the finite differences. The videos that we have done earlier. For this video, we're gonna talk about Newton forward interpolation formula. For for this is actually this is where actually interpolation starts. Now we have taken a function again y is equals to fx, which takes up values like y0, y1, y2. With now we already know that interpolation requires the values that says that for every x value we have a corresponding y value. It has to be, it can be more, it can be less, but we always have an x. For every x there is a y value, and so to this y naught, to this y0, y1, y2, there is a corresponding value of x naught plus h, x naught plus 2h of every x. Suppose now that we have to find fx for, and for this equation x is equals to f0 plus ph. Now what is p? It is same as n, which was we have declared in the last video. P is also any sort of real numbers. Now for any real number p, we have defined e. Now e, you know, e was our shift operator. So this e to the power p fx is equals to fx plus ph. Now e to the power p fx was p y to the power p, which we have done in the central difference. The shift operator was written in the same manner. We could get there. I'm sorry. We didn't go. We already have seen here the e to the power n yx. We have seen e to the yx is equals to x plus 1. That's how we had a generalized equation with y. In the same manner, we are changing the value of in the same manner, we are changing the value of e to the power p fx by yp to get a value of to get the value for x0 plus ph. From the relationship, as you can see, e is equals to 1 plus delta. We have already seen all the operators relationship. E is equals to 1 plus delta was a relationship that we have discussed in the previous video. All the operator relationships, and so here we use this relation e is equals to 1 plus delta to get this equation 1 plus delta p y to the power p y naught. And if we open this we open this relation through the binomial theorem, we would get a structure, a equation like 1 plus p to the p delta is plus p minus 1 divided by 2 factor into the second forward difference, and that's how we would get the whole equation. Now this is how we would take out the value of y p is equals to y naught plus p. We would just multiply the value of p y naught here, and to get a generalized value of y to the y p. Now if pi y is equals to fx, it was a polynomial with the nth degree. then all the higher differences n plus 1 and higher differences will be 0. Hence, if we hence in this whole equation will become like the this equation. Now this was the forward interpolation formula. This was Newton's forward interpolation formula, where we took the interpolation thing. I mean, the first video that I have explained what was interpolation. We have take that situation and we found the value of x is equals to x naught plus ph, and which was then used here. I mean, we use relationship between E is equals to 1 plus delta to um, get an equation like p equation like this, and with this we would say that this is our actual uh, interpolation interpolating formula, which was Newton's forward interpolation formula. Now, there's a remark: this formula that we are using is for the values of y near the beginning of a set. I mean, we have a set, right? A tabulated value. And uh, this interpolation method is only used for the beginning, like for x0, y0, or it is between x0 to x2, so that we could get this was about forward, right? So for the always remember, the forward interpolation is used for the beginning and the backward is used for the ending. It was the beginning of a set is said to be interpolated with the values, and it also extrapolate the values of y a little backward, means to the left of uh, y naught. I mean, we have the beginning of the set and the data set, which data points that are lying I mean above the y naught. I mean above all the data points. It is before the, I mean they are after the uh, y naught. They are after the y naught. They are extrapolated little backward. They are to the left of the y naught. This is why we use the forward differences, forward interpolating polation formula. This is also known as Newton-Gregory method, and Newton-Gregory forward interpolation formula. And this is how we have taken out all the values, and with this we could say that the generalized form of the whole formula is yp is equals to y naught plus p delta y naught plus p minus 1 divided by 2 factor uh, 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 second forward difference y naught plus this would go on till p minus 1 to p minus n minus 1 by n factor delta to the power n y naught. This would give us the whole value of our data set, the only this data set of the beginning, and a little backward to the left of y naught. Just like in forward interpolation, we have taken a function here y is equals to fx, taking a values of y0, y0, y1, y2 corresponding to the values of x0, x0 plus h, x0 plus 2h of x. I mean, interpolation says that we have to take the whole situation just the same in the same manner. Suppose now again we evaluate a function for x is equals to xn plus ph, where p was any real number that we have chosen. Now, to get the value of this equation, xn plus ph, we would take the relationship of e to the power minus 1 is equals to 1 minus delta. We could say this from the shift operator video. I mean, I have already discussed the shift operator, where we have this equation, this relationship between the delta and nebula. And so with this relationship we could say yp is equals to fxn plus ph. Yp would be uh, yp could be changed with fx as fx pfx. We could say from e to the power minus 1 fx, it could have been turned to, it can be replaced by yp is equals to fxn plus ph. Now the fxn plus ph is can be written as e to the power p fxn. This could be written as that. I mean, we only put the values in the function y is equals to fx to get this function. Like the function of this equation would be only be taken out if we put the values in y is equals to fx. Now, as we put the values of x is equals to xn plus ph in fx, we would get this relationship of e to the power p fxn. Yes, from the shift operator uh, shift operator equation. Now we know the relationship between the operators. So to get this, we could say 1 minus nepla to the power minus p by n. We would get this from the uh, relationship between e and nepla. Now, now if we open this whole equation, we through the with the help of binomial theorem, we would get equation like 1 plus, this is 1 actually, 1 plus p to the power p into nepla p plus 1 by 2 factor nepla to the power 2 plus p plus 1 p plus 2 divided by 3 factor p to the nepla to the power 3 to yn. Now yn would be like this would be solved in a manner in the same manner of which is given in this equation. I mean, we have only opened this, right? We have to multiply yn into it, and so when yn is multiplied in this whole uh, equation, we would get an equation like this. And what is this called? This equation is called Newton's backward formula, as it contains yn and backward difference of yn. Okay, this is what is the generalized form of the whole equation. Okay, and again, for this formula is only used for the end of a set of tabulated values. Like for Newton forward interpolation, we have seen that the that formula is used only when we are interpolating a value for the beginning of the data set, the set of tabulated values. Now for this we are using the end values, I mean the xn values, xn and yn values of the for the interpolation. I mean the yn values are interpolated here, not the mid one or in the beginning one. We are only using the end of the set of tabulated values. It also helps in the extrapolating the values outside the data set of tabulated values. I mean if we have xn, we could get y. If we want to take out the value of yn plus 1, we could easily do that with the help of backward interpolation formula, as this it would have been more easier with the backward formula. um, this there is this table example where we have taken some distance of x and y, and we would uh, find the value of we have to find the value of x is equals to 218 and x is equals to 410. Now x is equals to 218 has to be is between 200 and 250. It is not in the end of the tabulated values, it is in the beginning of the tabulated and values. So for this we would use the forward interpolation, and for the uh, and for the 410 value we would use the extrapolation, I mean the backward interpolation, as it is a extrapolating method. Extrapolating means if the data set is outside the tabulated values, I mean the when the data set the points are outside the data points in given, it is said to be extrapolating. Like we have 400 and we have to take out the value of 410, so we would that is extrapolating point, as it is outside the data set given. And if we have to take, like we have 100, we have to take the value of 90, we have to it is also an extrapolating value because it is lying outside the data set given. For 90 we have to use an forward interpolation, and for 410 we have to use the value of for 410 we have to use the method of Newton backward interpolation. Now this is how we would use the difference table. I mean the difference table is same in the for the whole process. I mean it is the same for the finite difference. I mean the forward difference and the backward difference. The only change is that we use the objectives are different. For now we have the difference table of uh, forward difference, and we would take out the value of we have to take x0 is equals to 200 as it was written in the data set given here. 200 is the value is 15.204, and I mean the x was 200 and the value of y was 15.04, and the y naught value delta y naught value was x 1.77. And that's how we would take the whole, and we would take the Newton Newton forward interpolation formula to generate the answer for this value. For like p, how would we get p? We would x minus x naught by h, 18 by 50, and so you can see the whole procedure here. So this was an example that we have done. You can do it very easily because it's we just take out the value of all the tabulated. We just take the value of the tabulated value and put it in the difference table, and put the in forward interpolation or the backward interpolation for the whole process, and that's how we do the whole thing. And so the interpolation has three types, which was forward difference, backward difference, and divided difference. We have already talked about forward difference and backward difference in the last couple of videos, which we had the Newton's forward interpolation formula. We had the backward difference as Newton's backward interpolation formula, and so the for this forward and backward difference, they had a one thing in common, which was they have an equal set of the spaces between every tabulated value was equal. I mean to say the h was here equal. For divided difference, the coordinates are not equidistant. The coordinates in forward difference and backward difference are always equal. When it comes to divided difference, we do not have the coordinates as equidistance. Now, when we talk about data set, we generally have some data sets which are not equidistant. I mean, for in a reality data set, data set, we do not actually follow forward difference or a backward difference, as it is not required every time the data sets that we are given are equidistant. And so for that situation we have divided difference. Here the coordinates are not equidistant, and so we do not have any here, as we can say that x, if we take any x in between x0, x1, x2, x3 till xn, we when we subtract x1 minus x0, where we could say that x1 minus x0 is not equal to x2 minus x1. I mean that the difference between all these terms are not equal, and obviously every x is corresponding to every y through interpolation, for interpolation. And so if we write fx0 minus fx minus x1, if x0 and x1, we could say that fx1 minus fx0 is divided by x1 minus x2. This would give us a divided difference for divided difference formula. This is the actual formula of divided difference. It is fx0 fx1 is equals to fx1 minus fx0 divided by x1 minus x0, which would give the symbol of divided difference x0 x1 fx. Now the values lie in fx0 fx1 fx2, and that's how we would also take out for the value a second degree of divided difference fx0 fx1 and fx2, where we would fx1 and fx2 minus fx0 and fx1. Yes, just like we do in the forward differences, we take out the first degree of delta, then and from that first degree of delta we take out the value of second degree delta. And for here also, for every divided difference degree, we would take the first degree minus subtracted from the subtract them and get the value of the second degree, as you can see here. Okay, and that's how we would get the values of second degree divided difference. For third degree, in the same manner as forward difference, we should get the values for second degree divided difference, subtract both of them, and get the value for the third degree. In this manner, we would get a difference table for divided difference also, same manner as forward difference and backward difference. We would get a difference table. As you can see, we are getting a y minus y0 divided by x1 minus x0 to get a first degree of divided difference. In the same manner, when we are dividing y, the first degree of y1 and the first degree of y0, we are subtracting them by dividing x2 minus x0 minus x0 to get the difference, divided difference of second degree. In this manner, the whole difference table would be made, and that's how the difference table, divided difference would be created. And to get the values of Newton divided difference formula for unequal intervals, we have to first set the function and take the x value. We would take the divided difference formula that we have used in the last page, and we would try to use the equation that we have used above, and keep the values, I mean the x0, x1, x2 values in the equation, and find the value of the whole. We would get a equation like the forward differences, and that's how the whole divided difference would be calculated through all the process of creating the first degree and the second degree of different divided difference. We would get the second degree. We would get, after dividing after subtracting the second degrees, we would get the third degree, and somehow we would get the whole difference table. um, and the only thing different from the other differences is that divided difference is not equidistant. It is to get the values for non-equidistant set of tabulated values. And so with this Lagrange's interpolation formula. Now the various interpolation formulas derived so far being applicable only now previous interpolation formulas were only applicable to the equally spaced one. Now we have Lagrange's interpolation and divided difference to help us with the unequal intervals. The here also we take a function like y is equals to fx, and take the values of y0, y1 corresponding to every x is equals to x0, x1, xn. We get a formula of just like divided difference. We have a formula where we have some tabulated values of x minus x1, where we subtract every other term from the first value and divided by the term from the term that we had. Like if we are having the third term, the third term would be divided by every other term. I mean to say is that this is the whole formula of Lagrange's. I mean, here we can see that the first value x is equals to x1, x2, xn. I mean the x is a variable which is divided by every other term in the tabulated values. We are creating firstly the y0 value, the y1 value, yn value. Yn, y0, y1 would be all replaced by the fx values, and so we would get a generalized form of when we open the y is equals to fx values. We would actually just replace the values of fx by y. We can have this proof that it is done here. We would firstly it is like the y is equals to fx not x minus x1, x minus x2, x minus xn, and that's how we would create the whole polynomial form. Then we putting the x0 x is equals to x0 and y is equals to y0, just like we have done in every other formulas. I mean, this is a generalized formula. We have to get it to that, and the Lagrange's formula is actually a little cumbersome to learn, as it is a little difficult when it comes to computation. And it is, we have already known that the Lagrange's formula is applied whether the values of xi are equal spaced or not. It is not it is easy to remember but quite cumbersome to apply. It is easy to remember. We usually remember it, but as when it comes to tabulated formulas, which are like, we have tabulated formula for like ninth term or any term like a 10th term, it would be very cumbersome as we have to generate an polynomial for every other term that we are using. And so that's why it is easy to use, easy to remember, but very, it is difficult to apply. So we will refer to do divided difference. As you can see, we have an example of which can you see, you can have a look in the whole differences, and that's how we do the Lagrange's interpolation formula. We have a proof that you can see here. We take a polynomial and we just uh, keep all the values that we are given, like the set of tabulated values that have been given are enclosed in, and then we take out a value in general to have a generalized form of fx is equals to x minus x1 x minus x2 till x minus xn, and for every y term we have to take out the xn value, x value, and that's how we will do the fx value. And with this, the Lagrange's interpolation formula ends. Thank you for watching this video.